Let's remember what we know about the decimal number system. Suppose that we have a number like the one you see on your screen, 9704. How do we write that number using base 10 powers? Powers of 10, in other words. Well, that number is written as 9 times 10 to the power of 3 plus 7 times 10 to the power of 2 plus 0 times 10 to the power of 1 plus 4 times 10 to the power of 0. This is how we make up this number in the decimal number system. Now the question is, why are we so used into representing numbers into the decimal system? Why not try a different base? And the answer may be surprising. It is because we have 10 fingers. This is an answer that is both, it is half serious, half not. Regardless of the reason we actually are more familiar with the decimal system, the computer is not. The computer understands two states. And this is because it is an electronic machine and it works with voltage. So the states that the computer understands is high voltage and low voltage. For this reason, the binary system is much more appropriate for a language for the computers than the decimal system would be. What we're going to see in the following videos and lectures is how we can represent in the binary system positive integers, negative integers, and real numbers. Before we go further, it is important to point out that you will find it useful if you actually know the powers of 2 up to the 10th at least. Know, for example, that 2 to the power of 7 is 128, or 2 to the power of 9 is 512. These are numbers that will make computations and estimates in your life easier. So try to learn the numbers that you see on this slide. We will now go through an example to understand how we can convert a number that is expressed into the decimal system into the equivalent form in the binary system. And we are again going to see positive integer example. So take the number 15, the representation 1, 5 in the decimal system. How can we convert that number to its binary representation? We start with the largest power of 2. So what is the largest power of 2 that is inside 15? It's 2 to the power of 3, which is 8. Great, so we write down 2 to the power of 3 plus whatever remains, 7. Now we try to express 7 as a power of 2. How can we express it like that? It is 2 to the power of 2 plus 3. Then we try to express 3 as a power of 2, which is 2 to the power of 1 plus 2 to the power of 0. So by now we have written 15 as a sum of powers of 2. And we are going to actually make it even more detailed and multiply with 1 each of those powers of 2. 1 times 2 to the power of 3 plus 1 times 2 to the power of 2, etc. The binary representation will be those numbers that we multiply the powers of 2 by. In this particular example, we have 1s. These are the numbers that will be the binary representation of 15. And we put each of those 1s at the place of the corresponding power of 2. Here is what I mean. We start counting from the right to the left with the first position having index 0, because this is the lowest power of 2. So you can see that the orange one is placed at the rightmost position. Then the green one is placed at the position with index 1, since the previous position had index 0. The purple one, which is the one that multiplies 2 to the power of 2, is placed at position with index 2. And finally, the blue one is placed at position with index 3. Again, starting from the right, going to the left, we number the indices starting with 0, 1, 2, 3. So now we have come up with the binary representation of the number 15. Now go ahead and try an example for yourself. Try to write down the binary representation of the number 42. After you have completed that task, return to this video and we will actually see together the answer. Like we did before, we have written 42 as a power of 2. 2 to the power of 5 plus 2 to the power of 3 plus 2 to the power of 1. And then, very important step, we multiply by 1 or 0 every power of 2 in this sum, starting with 2 to the power of 0 up to 2 to the power of 5, because 2 to the power of 5 is the largest power of 2 inside 42. And now we take these ones and zeros, the factors by which we multiply the powers of 2, and we place them in the right order. So, because we're multiplying with 0, the lowest power of 2, 2 to the power of 0, we will put 0 at the rightmost position. We will put 1 right next to it, to the left, because 1 is the factor that multiplies 2 to the power of 1, and so forth. This is how we end up with the number 101010 as the binary representation of the decimal 42. Now, you may have already noticed, in a binary representation, we put at the right corner the number 2 to denote that this is a binary number. Similarly, for the decimal representation, it is common at the right down corner to put the number 10, or sometimes just the word 10, to denote that this is the representation of a number in the decimal system. Here is an observation to keep in mind. In positive integer representations and some of the negative integer representations that we will talk about later, an even integer always ends in 0. So at the rightmost position there will always be a 0 for an even integer, while there will always be an 1 for an odd integer. We will actually use this criterion in order to check whether a particular integer is odd or even later in the programs that we will be writing. Another important observation to keep in mind: the most significant bit is the leftmost bit. This is also true, obviously, in decimal representations, but sometimes with binary numbers we get confused. Always remember the leftmost bit is the most significant bit.